Hello, good afternoon to all of you. I hope all of you are doing well. So, in today's class, we'll begin with the third set of instructions, and the first instruction that we're going to discuss is RLC. Now, RLC instruction is capable of rotating the content of the accumulator towards the left hand side by one position. So RLC, the content of the accumulator are rotated towards the left hand side by one position. Now here, in case of RLC instruction, please listen to me carefully. Bit D7 is copied to both D0 and C carry flag. So in case of RLC, bit D7 is copied to both carry and D0. Now the byte requirement is it requires 1 byte, 1 machine cycle and 4 T states. Now hex code for the same is 07. Flag, carry flag is modified accordingly to bit D7 and sign flag, 0 flag parity and auxiliary carry are not affected. Now likewise the next instruction that we're going to discuss is RRC. Now RRC instruction, the content of the accumulator is rotated towards the right hand side by one position, that is bit D0 is copied to both D7 as well as carry at the same time. Again I'll repeat it. On execution of RRC, the content of the accumulator are rotated by one position towards the right hand side. Bit D0 is placed in both D7 as well as carry flag at the same time. So it requires 1 byte, 1 machine cycle and 4 T states. Now hex code is 0F flag. Carry flag is modified as per D0. Assign flag, 0 flag parity, auxiliary carry remains unchanged. Now RET. Now RET is one of the important instructions whenever you're executing subroutine. So on execution, the RET instruction, on execution of the RET instruction, the program sequence is transferred from the subroutine to the calling program. Again, I'll repeat it. On execution of RET instruction, the program sequence is transferred from the subroutine to the calling program. The 2 bytes that are there in the top of the stack, the 2 bytes that are there in the top of the stack is copied to the program counter, and then this address and the execution resumes from this particular address. So this is the role of RET instruction. So when RET instruction is executed, the program sequence is transferred from the calling from the subroutine to the calling program. The 2 bytes from the stack is loaded onto the program counter, and the program execution resumes from there. Now it requires 1 byte, 3 machine cycles and 10 T states. Again, I'll repeat it. It requires 1 byte, 3 machine cycles and 10 T states. And the hex code is C9, and the flags, none of the flags are affected. Now RET is an unconditional return. Now likewise we have conditional return, that is RC. Now RC, on execution of RC instruction, the program sequence is transferred from the subroutine to the calling program if the carry flag is set or carry flag is equals to 1. Again, I'll repeat it. On execution of RC instruction, the program sequence is transferred to the transferred from the subroutine to the program if the carry flag is set or carry flag is equals to 1. If carry flag equals to 0, then no transfer takes place. Now, byte requirement, it requires 1 byte, 1 machine cycle and 6 T states if a condition is not true, and it requires 1 byte, 3 machine cycles and 12 states T states if the condition is true. Now hex code is D8 and flag is flags, none of the flags are affected. Now, likewise, we have another instruction that is called as RNC. So, it stands for return on no carry. So, on execution of RNC instruction, the program sequence is transferred from the calling from the subroutine to the calling program if carry flag is not set or carry flag is equals to 0. Now, if carry flag is equals to 1, then no transfer takes place. Now, the byte requirement, the machine cycle and T states are, it requires 1 byte, 1 machine cycle and 6 T states in case if the condition is not true, and it requires 1 byte, 3 machine cycles and 12 T states if the condition is true. Now hex code is D0 and the flags, none of the flags are affected. Now likewise we have RP instruction, return on plus or positive. So on execution of RP instruction, the program sequence is transferred from the subroutine to the calling program if the result is positive or sign flag is equals to 0. If sign flag is equals to 1, then no transfer takes place. Now it requires 1 byte, 1 machine cycle and 60 states if the condition is not true, and it requires 1 byte, 3 machine cycles and 12 T states if the condition is true. Hex code is F0, flags, none of the flags are affected. Now RM, now it stands for return on minus. So on execution of RM instruction, the program sequence is transferred from the subroutine to the calling program if sign flag is equals to 0, sign flag is equals to 1. If sign flag is equals to 0, then no transfer takes place. It requires 1 byte, 1 machine cycle and 60 states in case if the condition is false, and it requires 1 byte, 3 machine cycles and 12 states in case if the condition is true. Now RPE, stands for return on parity even. So on execution of RPE instruction, the program sequence is transferred from the subroutine to the calling program if parity is even or parity flag is equals to 1. If parity flag is equals to 0, then transfer of control does not take place. So it requires 1 byte, 1 machine cycle and 60 state if the condition is not true, and it requires 1 byte, 3 machine cycles and 12 T states if the condition is true. Now the hex code is E8 and the flags, none of the flags are affected. Now likewise we have RPO. Now RPO stands for return on parity odd. So the program sequence is transferred from the subroutine to the calling program if the parity is odd or parity is equals to 0. If parity is equals to 1, then no transfer takes place. Now bytes, machine cycle and T state. So it requires 1 byte, 1 machine cycle and 6 T states if the condition is false, and it requires 1 byte, 3 machine cycles and 12 T states if the condition is true. Now hex code is E0 and flags, none of the flags are affected. Now likewise we have RZ. Now, on execution of RZ instruction, the program execution or the program sequence is transferred from the subroutine to the calling program if the result is 0 or 0 flag is equals to 1. If 0 flag is equals to 0, then transfer does not take place. Now it requires 1 byte, 1 machine cycle, 60 states if the condition is not true, and it requires 1 byte, 3 machine cycles and 12 states if the condition is true. Now likewise, hex code is C8 and flag, none of the flags are affected. Now R and Z, return on no 0. So the program sequence is transferred from the subroutine to the calling program if 0 flag is equals to 0, right? Or if the result is not 0 or 0 flag is equals to 0. If 0 flag is equals to 1, then return does not take place. Now it requires 1 byte, 1 machine cycle and 60 states if the condition is not true, and it requires 1 byte, 3 machine cycles and 12 states if the condition is true. And the associated hex code is C0 and flags, none of the flags are affected. Now next instruction that you have is RIM, that stands for read interrupt mask, right? Okay, so here the instruction is used to both read in the status of the interrupt 7.5, 6.5 and 5.5, and also as well as to read in the serial input data bit. Okay, an 8-bit word is read in and stored in the accumulator. The layout of the word is shown in the figure. In the figure below, right? So in the RIM instruction on execution, this instruction is used to both read in the status of the interrupts, that is 7.5, 6.5 and 5.5, as well as to read in the serial input data bit. An 8-bit word is read and it's loaded onto the and stored into the accumulator or loaded onto the accumulator, and the the layout of the word is as follows. The first bit is SID, that is serial input data bit, and the second one is the second, third and fourth, so that is I 7.5, 6.5 and I 5.5 is the whether the interrupts are pending or not. So if bit is equals to 1, then interrupt is pending. Then you have interrupt enable flag, IE, right? And then you have mask bits for 7.5, 6.5 and 5.5. So that's interrupt mask. So if the bit is 1, then it's masked, the interrupts are masked. So here a RIM instruction is used in order to read the status of the various interrupts, that is 7.5, 6.5 and 5.5, as well as the serial input data. So what you need to remember is you need to remember the configuration of the accumulator after the execution of the RIM instruction, right? So this is very much important. So you need to remember the bit positions, that is serial input data bit, all right? So that is these D7 or the first bit, right? Okay, then interrupt pending bits, right? Then interrupt enable and interrupt mask bits. So it requires 1 byte, 1 machine cycle and 4 T states. The hex code is 20 and the flags, none of the flags are affected. Now likewise we have another instruction that is called as RST. Now RST instruction, so RSTN, so where n can have values between 0 to 7. Now on execution of RST instruction, this instruction operates like call instruction that goes to one of the 8 predefined memory locations on page 0. Each instruction that is RST0 to RST7 goes to a specific address location, right? Okay, so whenever RST instruction is executed, what we need to have is we need to have the associated RST number. So based on that, what we do is we go on to either of the 8 predefined memory locations from where the subroutines are executed, right? So the associated address for RST0 is 0000. For RST1, it is 0008. Likewise, RST2 is 101820283038. So how do we achieve the restart address is by multiplying the number with the associated number with RST instruction with 8. So 8 into 0 is 0, 8 into 1 is 8, 8 into 2 is 16. So 16, 10 is 16 in hex. Now then 8 into 3 is 24. So 18 is 1 8 is the representation of 24 in hex. So likewise we have 32, then we have so we have 0, 8, 16, then 24, then 32, then 40, right? So that is the way how what we do is we achieve the address by multiplying the RST number with 8. Now the byte requirement, machine cycle and T state requirement. So it requires 1 byte, 3 machine cycles and 12 T states. The associated hex codes are given with the respective RSTs, and no flags are affected. Now SBB instruction, SBBR. So now SBBR instruction on execution, the content of the register and the borrow flag is subtracted from the content of the accumulator and the result is stored in the accumulator. Again, I'll repeat it. SBB instruction, what does it do? It subtracts the content of the register along with the borrow flag from the content of the accumulator and stores the result in the accumulator. It requires 1 byte, 1 machine cycle, and 4 T states. The associated register combination with SSB along with the associated hex codes are specified for per user. So all the flags are affected based on the result of the operation. Now next one we have SBBM. Now what the SBBM instruction on execution does is on execution of SBB instruction, the content of the memory location pointed to by HL pair and the borrow flag is content of the memory location pointed to by HL pair and the content of and the borrow flag is content of the borrow flag is subtracted from the content of the accumulator and the result is stored in the accumulator, right? So SBB instruction on execution subtracts the content of the register along with the borrow flag from the content of the accumulator and stores the result in the accumulator. Now it requires 1 byte, 2 machine cycles and 7 T states, right? And the respective hex code is 9E and flags, all the flags is affected based on the result of the operation. Now SBI data, right? SBI data. So what does this particular instruction do is this particular instruction subtracts 8-bit data and borrow from the accumulator and the result is stored in the accumulator. Again, I'll repeat it. It subtracts 8-bit data 8-bit data and the borrow flag from the content of the accumulator and the result is stored in the accumulator. Now it requires 2 bytes, 2 machine cycles and 7 T states. Now the associated hex code is DE and flags, all the flags are affected based on the result of the operation. Now SHLD. Now SHLD, so the content of the register L are stored at the memory location specified. The content of the register L are stored in the address location specified, and the content of the register H is stored in the next memory location by incrementing the operand by 1. So here SHLD instruction on execution stores the content of the stores the content of the register L to the address location specified, and the content of register H to the address location obtained by incrementing the memory address by 1, right? Okay, so the content of register H are stored in the next memory location by incrementing the content of the operand by 1. So it requires 3 bytes, 5 machine cycles, and 16 T states. The respective hex code is 22, and flags, none of the flags are affected. Now, likewise, in contrary to RIM, we have SIM instruction. Now, this instruction is used to set the interrupt mask as well as the serial output data bit. The accumulator, the layout of the accumulator is as follows, right? So SIM instruction, so RIM instruction is capable of reading the interrupt mask as well as the serial output serial input data. Now here, SIM instruction is capable of setting the interrupt mask as well as serial output data. Now here, the configuration of the accumulator is as SOD, that is serial output data, then SDE, serial data enable. So if it is 1, then the data is enabled. Then R7.5, that is reset R7.5 flip-flop. Then MSE, then mask set enable. So if it is 1, it is enabled. Then you have M7.5, 6.5, and 5.5. This interrupt enable. If bit is 1, then the interrupt. So interrupt is masked. So if the bit is, if the positions are having in bit 1, then the interrupts are masked, right? So this is the orientation or the configuration of SIM instruction. So SIM instruction is used in order to set the interrupt mask as well as set the serial output data bit. Now the accumulator, the configuration of the accumulator as per the SIM instruction is, again I'll repeat it, SOD, SDE, then you have R7.5, then mask set enable, and then M7.5, M6.5, and M5.5. Now the byte requirement, machine cycle requirement in T state. So it requires 1 byte, 1 machine cycle, and 4 T states. And the hex code is 30, and flags, none of the flags are affected. Now SPHL. Now SPHL instruction on execution, the content of the registers H and L are loaded into the stack pointer. Okay, again I'll repeat it. And the content on SPHL on execution, the content of the register pair H and L are loaded onto the stack pointer. H is loaded onto the higher order part of the address, while L is loaded onto the lower order portion of the address. So that is what SPHL does. SPHL instruction moves the content of H and L register to the stack pointer, H to the higher order address, and L to the lower order address. Okay. Now bytes, so it requires 1 byte, 1 machine cycle, and 60 states. Hex code is F9, and flags, none of the flags are affected. Now STA instruction. Now STA instruction, STA 16, so it works with 16-bit address. STA instruction is capable of storing the content of the accumulator to the 16-bit address specified in the instruction. Again, I'll repeat it. The content of the accumulator is stored to the address location specified in the instruction. Now, bytes, machine cycle, and T state requirements. So it requires 3 bytes, 4 machine cycles, and 13 T states. Again, I'll repeat it. It requires 3 bytes, 4 machine cycles, and 13 T states. Hex code is 32, and flags, none of the flags are affected. Now, the next instruction that you have is STAXRP. Now, it works only with BC or DE pair. So STAXRP. So what does it does? What this particular instruction do is, on execution, it stores the content of the accumulator to the address specified in the register pair, right? So the content of the accumulator are stored in the memory location pointed to by the register pair. So the content of the accumulator is stored in the address specified in the register pair. So the content of the accumulator is not affected. Now, so likewise, it requires 1 byte, 2 machine cycles, and 70 states. Now hex code are 02 and 12. That is for BC and DE pairs. So none of the flags are affected. Now STC. Now STC instruction, it sets the carry. So the carry flag is set to 1. Now it requires 1 byte, 1 machine cycle and 4 T states. Now hex code is 37 and flags, only the carry flag is affected. Now the next instruction that you have is SUBR. So on execution, SUBR is capable of subtracting the content of the register from the content of the accumulator, and the result is stored in the accumulator. Again, I'll repeat it. On execution, SUB instruction is capable of subtracting the content of the register from the content of the accumulator, and the result is stored in the register. Now, bytes, machine cycle, and T states requirements. So it requires 1 byte, 1 machine cycle, and 4 T states. Now, the possible combination of SUB with the registers along with the associated hex codes are placed for your perusal. Now, all the flags are affected based on the result of the operation. Now, likewise, SUBM. Now, SUBM on execution is capable of subtracting the content of the address location pointed to by HL pair from the content of the accumulator, and the result is stored in the accumulator. Again, I'll repeat it. On execution, SUBM instruction is capable of subtracting the content of the address location pointed to by HL pair from the content of the accumulator, and the result is stored in the accumulator. Now, byte requirement, a machine cycle and T-state requirements are one. It requires 1 byte, 2 machine cycles, and 7 T-states. Now, hex code for SUBM is 96, and all the flags are affected based on the result of the operation. Now, the next instruction that we have is SUI data. Now, what it does basically do is, on execution, SUI instruction subtracts the 8-bit data from the content of the accumulator, and the result is stored in the accumulator. Again, I'll repeat it. The 8-bit data, immediate data, is subtracted from the content of the accumulator, and the result is stored in the accumulator. Now it requires 2 bytes, 2 machine cycles, and 7 T states, and the hex code is D6 flags. All the flags are affected by the result of the operation. Now the next important instruction that we have is called as XCHG. Now what it basically does is, on execution XCHG instruction, the content of register H and register D are exchanged. Likewise, the content of register L and register E are exchanged. So what basically does, it basically exchanges the content of the HL pair with DE pair, H with D and L with E. Now it requires 1 byte, 1 machine cycle and 4 T states. And the hex code is EB, and flags, none of the flags are affected. Now the next instruction that you have is XRAR. Now XRAR instruction on execution performs exclusive OR between the content of the register and the content of the accumulator, and the result is stored in the accumulator. Again, I'll repeat it. XRAR instruction on execution performs exclusive OR between the content of the accumulator and the content of the register, and the result is stored in the accumulator. It requires 1 byte, 1 machine cycle, and 4 T states. Now, the possible combination of XRAR with the registers are specified along with the associated hex codes. Now, zero flag, sign flag, parity flag are affected based on the result of the operation. Carry flag and auxiliary carry flag are reset. Now, likewise, you have XRAM. So, XRAM instruction performs exclusive OR between the content of the address location held by HL pair and the content of the accumulator, and the result is stored in the accumulator. Again, I'll repeat it. On execution, XRAM instruction performs exclusive OR between the content of the address location held by HL pair and the content of the accumulator, and the result is stored in the accumulator. Now it requires 1 byte, 2 machine cycles, and 7 T states. Now hex code is AE, and flags, zero flag, sign flag, and parity flag are affected by the result of the operation. Carry flag and auxiliary carry flag are reset. Now XRAI 8-bit data. Now XRAI instruction on execution performs exclusive OR between the 8-bit data and the content of the accumulator, and the result is stored in the accumulator. It requires 2 bytes, 2 machine cycles, and 7 T states. And the hex code is, associated hex code is EE. Flags, zero flag, sign flag, and parity flags are affected by the result of the operation, whereas carry flag and auxiliary carry flag are reset. Now the next instruction in the one of the important instruction that we have is called as XTHL. Now XTHL, the content of the register L are exchanged with the stack pointer. The content of the register L are exchanged with the stack location pointed to by the stack pointer. The content of register H are exchanged with the stack location pointed to by the stack pointer plus 1. Now the stack pointer remains unchanged. So here what happens is that on execution of XTHL instruction, the content of the register is exchanged with the stack location pointed to by the stack pointer, and the content of H is exchanged with the stack location pointed to by stack pointer plus 1, and the stack pointer remains unchanged. So it requires 1 byte, 5 machine cycles, and 16 T states. Now the hex code is E3 and none of the flags are affected. So till now in today's class, what we have learned is we have learned almost 30 to 31 instructions along with the description, the byte requirement, the machine cycle requirement, the T-state requirement, the associated hex code, and flags. So we'll end our instruction set in today's class. So we'll meet up in the next class where we will be discussing interrupts of 8085, interrupts associated with 8085. So thank you very much.